Okay, this is continuing on with lesson 2.2, and here we're proving theorem 2.3, the limit of a sum, and this theorem is stating, suppose the limit of one function f of 1 x equals to limit 1 as x approaches a, and then we have a second limit f of 2x is equal to a limit sub 2 as x approaches a, some number a, and we define g of x as the sum of f of 1 and f of 2. Then, in that case, the limit of our sum, g of x is equal to limit as x approaches a is equal to limit 1 plus limit 2. So the sum of the limits of our functions are equal to the sum of the limits of each function. All right, so before we start, we want to recall the limit as x approaches a of our function, just any function f of x, equals to a limit. This means that for all epsilon greater than 0, this backwards looking e means there exists a delta greater than 0. St means such that all x is in the element of all real numbers with the absolute value of x minus a is greater than 0 but less than some number delta. We have a absolute value of f of x minus its limit is less than some number epsilon is less than epsilon. Well, what all does that mean? On the graph, we have this curve, okay? And let's say this curve, make this a little bit, let's say we have something like this. And we have, as x approaches, here's our function f of x. As x approaches a, right, then you're going to reach a limit. Well, if we don't know, what we're trying to do is we're trying to establish a range from that delta being some number. So this would be a plus delta, right? And this would be a minus delta, where delta is some number where you get a range. Well, that's going to produce an epsilon, a range for epsilon. And so this would be L minus some number epsilon and L plus some number epsilon, where epsilon is the range of numbers that's getting closer and closer. So as x approaches a, then your limit approaches somewhere, approaches as x approaches a, then you're getting closer and closer to your limit. But if we don't know what that range is, right, we want to establish, so that's where this is x minus alpha is less than some number delta, and this is going to be our function. The difference in our function is going to be less than some number epsilon. Okay, so we're trying to prove this. So we're constantly looking at these two values when we're working with limits. All right, so continuing on, our proof is let epsilon be positive. Okay, some positive number, since the limit as x approaches a for f of 1 is equal to L1, then there exists a delta, we call delta 1 is going to be positive or greater than 0, such that for all values x that are real numbers or elements in the real number set, with our difference from x to some number a is going to be less than delta 1, then we have our f of x, our absolute value of f1 x minus limit 1 is less than epsilon over 2. Now we're going to use epsilon over 2 because we're looking at a sum here of these two limits, okay, f1 and f2. So we need to come up with epsilon over 2 and epsilon over 2 to give us an epsilon. And since we have the difference in x minus a is less than delta 2, then we have the absolute value of f2 x minus our limit 2 is less than epsilon over 2. We'll call that 2, 1 and 2, epsilon over 2, 1 and epsilon over 2, 2. And also we define delta as being the smaller of delta 1, the set, and delta 1 and delta 2. So we can go smaller, and that's okay. We can define it as smaller. So we want to choose the smaller of the two deltas. Then we can say that the absolute value of g of x minus the sum of L1 plus L2 is less than, is going to equal to f1 x plus f2 x, and we'll put brackets here, minus L1 plus L2, because we're going back to using, instead of f1 equals f1 x minus the limit is less than epsilon over 2, we're going ahead and putting the sum of those together. So from here we can, I'm going to go ahead and write up here, continue this up at the top. So from here, and that's absolute value, we're going to go ahead and distribute that negative. So that's going to equal the value of f1x plus f2x minus L1 minus L2. Okay, so all we did was we just distributed this negative. So now we want to get it to where, now we want to get this to where we're applying the difference of our function and our limit. We want to put these two together. So we're going to take limit 1 and f2 and switch places. So that's going to equal f1x minus limit 1 plus x minus limit 2 to that. Okay. Now, we already have from here the triangle where we just have f of x 1 minus L1. So in the triangle theorem, triangle theorem, and you can see this a lot. The absolute value of A plus B is less than the sum of the individual absolute value of A plus absolute value of B. Okay, so we can take this and split it. So that would make it less than or equal to the absolute value of f1x minus L1, and then absolute value plus the absolute value of f2x minus L2. Okay, so since we said before that f1x minus L1, the absolute value is less than epsilon over 2, and we said that the absolute value of f2x minus L2 is less than epsilon over 2, then we can just substitute epsilon over 2, 1, and epsilon over 2, 2 in for each one of these. So this is going to equal, this is going to make it, that means that this is less than epsilon over 2, epsilon 1 over 2, and this one is less than epsilon 2 over 2. So epsilon 1 over 2 and epsilon 2 over 2 is equal to epsilon. And so we've shown that we've got to this. So as long as we can prove this, then we've proven our theorem, which we've done there. So in summary, we can say that since we choose a delta to be the smaller, of delta 1 and delta 2 and delta 2, because each one of these will be x minus a is less than delta 1, and this dx minus a is less than delta 2 for each one of these to correspond with this, our delta and our epsilon, they go together. So we're saying that the sum of these, that the delta of these two, we're going to choose the smaller one, and then we can say that 0 is greater than x minus a, which is less than delta, so we're choosing the smaller one, with epsilon 2 plus epsilon 2 for 1 and 2 is equal to epsilon. So we've proven that way back here that the sum of our functions minus each one of their limits, we get an epsilon. And so x minus a, we have that difference in x, for the difference in the distance from x minus a is less than delta, and we get an epsilon. So once we do that, then we've proven it, and that's the end of our proof. And that's how you're going to prove the homework in the same way.